All right, here we are for Honors Physics Universal Gravitation Worksheet 3, Problem 7. Okay, so take a look at the problem. It says, the International Space Station typically orbits the Earth at a distance of 380 kilometers above the Earth's surface. Calculate the acceleration due to Earth's gravity at that distance. The radius of the Earth is 6,371,000 meters, and its mass is 5.97 times 10 to the 24th kilograms. Is an astronaut actually weightless at this distance? So here we go. Problem 7. So the setup then is you say, hey, we've got this satellite orbiting the Earth, this astronaut orbiting the Earth, some distance above the surface. So if we draw a little sketch, right, of course, always a good first step to solve a problem. You say, here's the Earth. And then we were told that this radius is 6,371,000 meters. 6,371,000 meters. Now, the satellite isn't at the surface, right? Of course. The International Space Station is what we're dealing with. Of course, the astronaut on the ISS. So the astronaut, ISS is up here, right? Some solar panel. That's not drawing a fancy picture. Anyway, so it's up there. Now, they tell you that this is 380 kilometers above the Earth's surface. So that means this distance, 380 kilometers, that's 380,000 meters. So the key thing we realize here is that I'm trying to find the acceleration due to gravity. Is that right? Yes, the acceleration due to gravity, the little g value is what we're trying to find. So of course we would set up, hey, sigma f is ma, right? And when we do this for an object up here, we say the only force acting on it is that gravitational force from the Earth. And so we say, okay, that gravitational force is equal to mass times acceleration centripetal, right? Or better yet, we just want the gravitational field strength. That if it's just gravity pulling, the acceleration would be g. It'll be the g value at that point. Now it is also, that's true, that is also the centripetal acceleration for it that's making it turn around the orbit. But we're not doing an orbit calculation here yet. Okay, so take a look at this. The gravitational force, we're going to pull out Newton's law of universal gravitation for that. And so we're going to say, okay, that gravitational force, that would be big G, m1, m2 of r squared. Our masses, one is the mass of, well, I guess we're going to just say the space station, right, of the ISS, International Space Station. Mass of the Earth over, now what about this r squared? Well, what this r means is it's a distance in the radial axis, really, radiating out between the object from the object. Distance along that, that's what matters, is the distance along that radial direction from the object. So we're trying to find this distance between the middles of these two objects is the idea. And so you say, well, that distance, it's not just the radius of the Earth, it's not just the 380,000, it's both of them together, this whole distance. So for the r there, right, that's going to actually be, as it turns out, the radius of the Earth and the height above the Earth's surface combined is that distance we have to square. Over here, the mass is the mass of the thing that's accelerating, the thing we're accelerating inward. That's the International Space Station. That's the thing we're analyzing here. Okay? So mass of the ISS. Okay? And then times G. Okay? We notice that the mass of the International Space Station is on both sides of the equation, so it's going to drop out. Bam, bam. And what's left is we can find the g value there, okay? Again, this is not going to be 9.8 because we're not at the surface of the Earth. What's interesting, though, is how does that acceleration compare to the acceleration at the surface? At the surface, we know it's 9.8, right? We're expecting it's going to be less because we're moving them farther away, right? But the question is how much less, right? So if I do this calculation, right, let's put the values in, big G, 6.67 times 10 to the negative 11, always, universal constant. Mass of the Earth, they're telling us, is 5.97. That's what they like us to use in this problem. 5.97 times 10 to the 24. And I'm going to divide by that distance. That distance is going to be adding these two numbers together, right? Can I do that in my head? Yeah, sure I will. So that's going to be 6, and then 3 and 3, that'd be 6, but we're going to go once, so it'll be 6, 7, 5, 1, right? Times 10 to the 6th. I'm going to square that. All right, so yeah, okay, yeah, I feel good about that. Okay, so that's it. That's going to be the value for G there at that point in orbit. Okay, at that point in orbit, what the G is going to be. Okay, where the ISS is, when the International Space Station is. So if we go ahead and punch that in the calculator, right? Now, when I do this, I can go ahead, I can use my trick here of separating out the powers of 10. That's just the way I like to do it. If I do that, the powers of 10, 10 to the minus 11 times 10 to the 24, that'd be 10 to the 13. 10 to the 6 squared, that'd be 10 to the 12. 10 to the 13 or 10 to the squared. I'm just going to take what the calculator tells me and I multiply, do these times 10. 10 to the 1. So here we go. 6.67 times 5.97 divided by 6.751 squared. Okay, and then times 10 to the 1. I'm going to end up with 8.74. So you look at that and you're like, hey, at the surface of the Earth, the acceleration due to gravity is 9.8. And here it's 8.74. You say, hey, that's not that different. 9.8, 8.7. They still have the bulk of their weight at that point. The Earth is pulling on them, right? In fact, if you go ahead and you take that answer and I do it over, I'm going to go one more digit down, over 9.81, right? Because that's the acceleration due to gravity of the Earth is typically closer to 9.81 meters per second squared. That's 89% of the gravitational force that it would be on Earth. 89% at the surface at that point. Like, oh my gosh, they would still have 89% of their weight, astronauts in the ISS. Why do they appear to be weightless? Why do they float around up there? And we've talked about this. We said, hey, it's not that they don't have gravity acting on them. Gravity is acting on them. That's what makes them bend to the orbit, right? They wouldn't be changing their direction if there wasn't a force pulling them inward, right? Okay, that gravitational force pulling in. They still have to have that force. But why do they seem to be weightless? Why do they float around in the station? You say, well, it's because the station is being pulled in and accelerated in the same rate they're being accelerated in. One of them is not accelerating faster than the other and slamming into the other. They're just falling next to each other, basically. It's like we said, it's like a projectile, and we said it's falling, but it just has to be moving sideways at the same time. And because the curve of the Earth matches the curve of your path, you never get any closer. Okay, and that gravitational force is being redirected always toward the center, toward the center, toward the center. So it's always perpendicular to velocity, so you just continue going around in a circle, right? It's not making it get faster or slower, you're just going constant speed in a circular orbit. And that is that problem. So they're weightless because they're falling, and the container they're in, the space station they're in, it's falling too. And so you're not trying to go faster than it. You're not running into it, pressing into the surface at all, right? And so you're just moving through it. There's no normal force on you. You don't feel like you're being pressed into the floor, and so you don't feel like you have any weight. And that's it, okay? And that's why astronauts are weightless in orbit, which is something that I think is actually really kind of neat once it clicks and you see that that's how it works. Is that they're falling, right? And that's why they're weightless. It's not that they're far away. They're so far away. They're not that far away. 380,000 out of 6 million, you know what I mean? That's like what percentage of the radius of the Earth further out? You know what I mean? If I wanted to draw this picture to scale, right? 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 You're like that's only 6% of the radius of the Earth further out. You know what I'm saying? So if this was like, if this is, you get it, right? So like if I drew this to scale, right? Where does that International Space Station orbit? Drawn to scale in this picture, it orbits like there, right? Okay. It's not that much further out. It just has to be above the atmosphere, above the air. Why would they spend all the energy and fuel to lift them up higher than they need? They just put them up above as much of the atmosphere as they can, so there's not that drag from the atmosphere. So they minimize that. That's really it. So yeah, so it's not that they're far away from the Earth, and that's why they're weightless. It's just they appear to be weightless because they're falling. All right, that's it.